financial conversations.
Good afternoon. I hope you can see the screen and hear us.
Yes, we can see it.
My name is Karina Olaru, and today I'll be presenting alongside my colleague Andrei Ghiurțu. We are from Transylvania University of Brașov, and as you can see,
the title of our project is Optimizing
One
Language
second.
Models for...
Karina, we cannot...
Okay, sorry for that. Okay.
These are the
topics.
topics. It's okay,
It's okay, the sound now. Okay, sorry. So this is the table of contents, and I will move on with the next slide. What was the motivation for starting this project? Andrei and I began working on a mobile application for personal budget management and thought about what interesting features we could add to such an application. And lately there is a trend towards AI solutions, but we wanted to build something educational and truly useful for the users. So we started to work on this language model, a financial advisor, and these were our main objectives. We wanted to start with a base model that we could train on financial data, so it would be specialized in this domain. And also this module is intended to be integrated into a mobile application. So it needs to run with limited resources directly on the user's device to ensure data protection. It's Andrei's turn now, but I think his mic is stopped. Can the next person please start so we can fix this issue? We're very sorry.
Karina, can you present Andrei's part?
Yes, I can try.
Okay.
Okay, so now for the pipeline. When the user asks a question, it's then converted into a vector embedding, which is compared with what we have stored in our vector database. the retrieved contexts are re-ranked, and the top 3 are appended to the user question. Then these 3 most important contents are then introduced in the XGEN fine-tuned model that then will create a response. That response then enters in a toxicity and hallucination pipeline, and that gives us a score. If the answer is not good, if it has hate speech or anything that we don't want to send to the user, then the model would give a generic answer. But if the answer is okay, then the correct answer would then go to the user. And now we will talk about the most important aspects of the application. First of all, the vector database. We used a platform named Quadrant to store our data. This data was fetched using different APIs, such as News API or FinHub. And here we have a diagram that illustrates how Quadrant works. But I will move forward. Now for the re-ranking mechanism, we just discussed how contexts are extracted from the vector database. It uses a bean coder to calculate the cosine similarity between the question introduced by the user and the context. However, we cannot be sure what the result would be, that if the result would be truly relevant for constructing the answer. Therefore, we added an intermediate module between the bean coder and the generative model. This module that we introduced is a re-ranking mechanism. While a bean coder calculates cosine similarity between the embeddings of the question and each context, a cross-encoder simultaneously inputs both sentences into the transformer architecture, BERT in our case, and calculates the relevance factor between them, which is then provided by the classifier. The BERT-based model was trained by us on a synthetic dataset. We used OpenAI APIs, and we sent a question and a context and asked for 5 sentences that fit the context and 5 sentences that don't. And the task of the model was to classify as accurately as possible the relevance between the question and each sentence. And this diagram explains how this re-ranking mechanism works. The user inputs a question, which is embedded, and the cosine similarity is calculated with the contexts in the database. The top 10 most similar contexts are extracted. These are then fed into the BERT cross-encoder, which outputs 10 relevance scores for the contexts related to the question. And using these scores, we reorder the contexts and forward only the top 3 to the generative model. Now, for the generative model, we used as a base model XGEN with 5 billion parameters, and this decision was influenced by the following requirements. Running on a wide range of mobile devices, so we wanted to have as minimum as possible number of parameters, and the model's capacity to retain as much information from conversations as possible. And because we couldn't find a data set that was fit for us to be to contain financial conversations, we also generated a synthetic data set. We used ChatGPT 3 and we trained it to respond to financial related conversations when provided a context. And also, we have a pipeline for detecting toxicity and hallucination. The toxicity detection model assigns a score for different categories of toxicity, and we have a threshold. that either lets the message to be overwritten or not. And similarly, the hallucination model provides a similarity score between the context, question, and answer. Now for different optimization techniques for large language models, there are numerous ones, but we explored two of them that I will present next. The first one is pass-through or depth upscaling, which involves merging certain layers from multiple models. And the result of this operation is a model with a larger number of parameters, but better performance. We will discuss about those graphs at the end of the presentation. That's why I skipped them. And now another technique worth mentioning is ties. This involves extracting the most significant weights from various models, each specialized in a certain domain, to form a final multitasking model. This technique is then combined with pruning, which means certain weights are randomly reset to their initial values, and rescaling, which means the new weights are merged with the initial ones using a scaling factor. And together these form their optimization technique. And here we included a diagram which better explains how their works. We have two models, for example, one specialized in math problems and one specialized in code. When we apply there, we only keep the most significant parameters from each model, and when merging them, we will have a resulting model which performs in math-related tasks as well as code-related tasks. And now for the performance metrics, we use a very popular benchmark for this called Massive Multitask Language Understanding. And we tested our model with multiple choice questions in these domains. And the models that we compared is the base GWEN, the first one. Then we have GWEN Financial QA, which is the model that we fine-tuned with our synthetic data set. And this one performed the best out of all four. We have a 13% increase in accounting, which is good because we wanted to create a financial advisor. So we wanted to perform good in accounting tasks. But it also has 8% increase in econometrics and 4% increase in macro and microeconomics. The third model is the GWEN model optimized using the DARE technique. This one performed good as well, but not as good as the financial QA. And the last one is the model optimized with pass-through. And now we have a short demo. And we can notice that our model tends to talk a lot, but it tries to explain thoroughly the context. And this question is related to AI, but we can notice that it still tends to touch the financial domain, even if the question is not really related to finances directly. And this is the end of the demo. And also the end of the presentation.
Thank you.
Thank you. Also, you will have to stop Andrei's presentation because his Teams is frozen and he cannot stop the sharing.
Okay. Next presentation will be